In this video, I'll talk about a paper I wrote in 2016. The title is Let Students Derive by Themselves Two-Dimensional Atomic and Molecular Quantum Chemistry from Scratch. In this paper, I solved the Schrodinger equation for the hydrogen atom and the hydrogen 2 molecule in the two-dimensional world. So you may find this paper by using this volume, issue, page numbers, or you may search for this paper by author name or title. And this is the web link of the paper. In this paper, I included a few appendices. The first one is the three-dimensional Laplacian operator in polar coordinates. It's very tedious to convert the three-dimensional Laplacian operator from the xyz Cartesian coordinates to the r, theta, phi polar coordinates. But I will quickly go over the procedure. So first, you need to express x, y, z in terms of r, theta, and phi. And then you can express r, theta, and phi in terms of x, y, and z. And then during my derivation, I use d instead of delta, although all the derivatives are partial derivatives. This is just for convenience. It's a bit more difficult to type delta and include the corresponding subscripts. So if you see delta psi over delta x or d psi over dx, you may assume y and z are held constant. And if you see d psi over d phi, you may assume r and theta are held constant. So let's first look at dr over dx. The result is sine theta cosine phi. And we can do dr over dy, dr over dz. Now we're going to do d theta over dx. We cannot do that directly. We do d cosine theta over dx first. We got this expression. And d cosine theta is negative sine theta times d theta. And then we get the expression for d theta over dx. Again, when you see d theta over dx, this is actually delta theta over delta x with y and z being held constant. And then we can do d theta over dy, it's right here, d theta over dz. Okay, it's here. And then we can do d phi over dx, d phi over dy, d phi over dz. So over here, this equation tells us phi only depends on y and x. So d phi over dz is just 0. And how do we get d phi over dx? We actually do d tangent phi over dx first. We get this. And then we solve this d tangent phi and see how this d tangent phi is related to d phi. So it's right here. It's right here. Okay, d tangent phi over d phi is 1 over cosine phi squared. So by using this equation and this equation, we will get d phi over dx. Similarly, we'll get d phi over dy. So this is d phi over dy. And now I'm going to summarize the 9 derivatives. dr over dx, dy, dz. d theta over dx, dy, dz. Finally, d phi over dx, dy, dz. Again, over here, phi does not depend on z. So now we'll use the chain rule. So we can convert the first derivative of a function with respect to x to, over here, how this function depends on r, theta, and phi. Well, why is that? If you change x, okay, over here, you're changing x, and you are trying to get the change of f. So how does this function f changes with x? Well, just treat r, theta, and phi as intermediate variables. So when you change x, you change r. When you change r, you change f. When you change x, you change theta. When you change theta, you change f. When you change x, you change phi. When you change phi, you change f. So that's why you get this equation. And then we can plug in delta r over delta x, it's here. Delta theta over delta x, it's here. Delta phi over delta x is here. All right, so now we successfully converted this first derivative with respect to x to the sum of three single variable derivatives with respect to r, theta, and phi. So again, let's try to make it a bit more convenient. So I'm going to just write df over dx instead of delta f over delta x by holding y and z constant. And this is my expression. So this equation is exactly the same as this equation. I am just being lazy here. I'm using df over dx for this partial derivative. I'm using df over dr for this partial derivative. All right. And now we have the operator. So d over dx, that's the first derivative operator, is equivalent to the sum of these three operators. And now let's look at the second derivative. The second derivative is the first derivative of the first derivative. We just need to apply this derivative twice to the function f. So once, twice to the f. And you can immediately see we have 1, 2, 3, 3 terms, 1, 2, 3, 3 terms over here. So really we're going to have a total of 9 terms. I'm going to label them 1.1, 1.2, 1.3, and then 2.1, 2.2, 2.3, etc. So 1.1, that means we're going to apply this to f first. Okay, and then whatever the result is, I'm going to apply this again to that result. So you get this thing here. What about 1.2? 1.2, that means we're going to apply this second term to f first. And then apply this first term to the result. So now you can see there are 9 terms. This is first term, second term, first term, third term, so etc., etc. So you can pause here and try to derive 1.1, 1.2, 1.3 yourself. And then you can pause here and derive 2.1, and then 2.2, 2.3 if you want to. Now you may pause here. You can derive 3.1, 3.2, 3.3. So we got all those terms, and we need to put them together. So let's look at the sum. So I put them together. This is 1.1, 1.2, 1.3, 2.1, 2.2, 2.3. 3.1, 3.2, 3.3. So a total of 9 terms. Actually, in 8 of these 9 terms, we have actually a combination of 2 terms. So in total, you are looking at 17 terms on the right-hand side. We can slightly simplify the expression, but still it's fairly complicated. So this is the second derivative of f with respect to x. Similarly, we can do y. I'm going to show you y here. So this is the first derivative operator with respect to y. And then this is how we do the second derivative. And again, there are 9 terms. We have 1.1, 1.2, 1.3. So you can pause the video here, see if you can derive this. And then we have 2.1, 2.2, and 2.3. All right. And then 3.1, 3.2, 3.3. And similarly, we put all those terms together. It looks very complicated. Make sure you don't make any mistake. And then we simplify the second derivative of f with respect to y. We got all this expression. Now, let's combine the 2 second derivatives. We can cancel many terms, combine some terms. If you do this carefully, you will get this result. I want to show you this here, and you can pause here and see all the expressions. And then this is after cancellation and simplification. So this is the sum of the 2 second derivatives with respect to x and to y. Now let's look at z. Using the chain rule, we have this for z. And for convenience, again, we're using d instead of delta. And we can get the second derivative of the function f with respect to z. It's just this. Now, finally, we're just combine x, y, and z all together. By the way, you can pause here, see if you can derive the second derivative with respect to z all by yourself. Now the Laplacian. So this is the Laplacian being applied to f. So we put all 3 second derivatives together. We get this final expression. So this is the final expression of the second derivative of f with respect to x, y, and z in terms of r, theta, and phi. So we did convert this Laplacian to the polar spherical coordinates. And also you can prove that this equation is equivalent to this equation. They are exactly the same. Alright, so I'm going to show you the derivation quickly. So we can go from here and then we can expand this one, and then we get this result. So again, this expression is exactly the same as this expression. Alright, you can try this yourself. Now I'm going to show you the two-dimensional Laplacian operator. So you saw the three-dimensional Laplacian operator. You saw its conversion to the polar coordinates. It's extremely tedious. There's no way to cover that in class. But somehow it's possible to cover the two-dimensional counterpart either in class or even ask your students to do the derivation. So now let's look at the two-dimensional Laplacian operator. So we have only x and y in the Cartesian coordinates, or r and phi in the polar coordinates. So this is how to relate x and y to r and phi. And dr over dx is simply cosine phi, dr over dy is simply sine phi. So we have much simpler first derivatives. Now second derivatives, d phi over dx and d phi over dy. So we can do d tangent phi over dx first, alright, and then evaluate d tangent phi over d phi. And put these two equations together, we get d phi over dx, alright. Similarly, we'll get d phi over dy. So this is d phi over dy. So in summary, we have this four first derivatives. How r depends on x and y, how phi depends on x and y. Now let's use the chain rule. So delta f over delta x is cosine phi times delta f over delta r, sine phi minus sine phi over r times delta f over delta phi. So again, this is because when you change x, you change r. And when you change r, you change f. When you change x, you change phi. When you change phi, you change f. So this is the chain rule. Now we have the expression for d over dx operator, d over dy operator. So these two are operators. Okay, so these two are first derivatives, and these two are first derivative operators. Now let's look at the second derivative. So we just need to apply the first derivative operator to this f twice. So first time you apply the operator to f, and then you apply the same first derivative operator again. What's the result? I'm going to pause here and see if you can get the same result. This is the result. It's still very tedious, but much better than the three-dimensional case. You can do the second derivative of f with respect to y here as well. Again, you have many terms, but it's simpler than the 3D case. Now put them together, we have a bunch of terms. I think we have 5 terms from y, 5 terms from x. Put them together, we have 10 terms. But put them together, you will dramatically simplify the Laplacian operator. The reason is very simple. Many terms cancel. So for example, this term and this negative term and this positive term cancel. Okay? And this negative term and this positive term cancel. And also, you know, sine phi squared plus cosine phi squared is 1. So, we got this expression. All right? And then this is the two-dimensional Laplacian in the xy coordinates, in the r and phi polar coordinates. Now let's try to solve the Schrodinger equation for the hydrogen atom in the two-dimensional world. So this is kinetic energy operator, potential energy operator, and this is the Laplacian in the two-dimensional world. So all we need to do is we need to solve this Schrodinger equation, and we'll do a separation of variables. Let's say the wave function is the product of a function of r and a function of phi. So we just plug it in and we do some mathematical simplification and the separation. We got this result. And both sides divided by r times phi. So this is just a wave function of the electron, and we can successfully separate phi from the variable r. So over here, the left-hand side only depends on phi. The right-hand side only depends on the radius r. How is that possible? It is possible only if both sides are equal to a constant. So we're going to say, well, this equals a constant. I'm going to set the constant to be L squared. The reason is this L, you're going to see, corresponds to the angular momentum quantum number in general chemistry. So we can solve this equation easily. Phi is e to the power of plus minus IL phi. Again, L is the angular momentum quantum number. And in this case, you may wonder, what is m sub L? Okay, m sub L can only be plus L or minus L. Nothing in between. So because we're talking about a two-dimensional world, if you know the angular momentum vector, it can only point up or point down. So there are only two possible values for m sub L. M sub L can be plus L or negative L only. So now we can solve the Schrodinger equation for this R as well. For the 1s orbital, so we're going to look at 1s, 2s, etc. L is 0, and then we have this equation to solve to get the this is the radial wave function, and we make a guess here. We take a guess about the form of this radial function. Because we learned the hydrogen atom in the three-dimensional world. Many mathematicians made contribution to that. So for now, we're going to just stand on the shoulders of these mathematicians, and we say maybe this R is also an exponential function of R. We just don't know the exponential component B. So B is a parameter. And this is our conjecture. We'll plug into this equation. Now we have a algebraic equation here. We solve this equation. We get B equals 2. Therefore, this R, this radial function, is e to the power of negative 2r. All right? And for the 1s orbital, the wave function does not depend on phi at all. So you got this wave function, e to the power of negative 2r. You got the energy. The energy is negative b squared over 2, so it's negative 2 atomic unit of energy. Now let's look at the 2s orbital. So for the three-dimensional case, you know the radial wave function takes this form. So again, we are taking a guess here. For the two-dimensional hydrogen atom, we're guessing maybe it's also taking this kind of form. It's r minus a constant times e to the power of negative br. All right, and then we plug it into this differential equation to convert it to a simpler algebraic equation here. All right, it's a little simpler. And then we solve this algebraic equation. We find this equation, and then B is 2/3, C is 3/4. So we got the wave function is R, it's R minus 3/4 times e to the power of negative 2 over 3 times R. So this is the wave function. And we can also calculate the energy, negative b squared over 2. This is just the eigenvalue you get, and you have this as the energy of the 2s electron, negative 2 over 9. You can also do 2p orbitals. For the 2p orbitals, you will have the radial function and angular function. So if we kind of solve this, we make a conjecture, and then we have this radial function. It's just r times e to the power of negative 2r over 3. We have the energy as well. So pay attention here. The 2p energy is equal to the 2s energy. All right. And we can verify our conjecture. We just plug in this wave function into the differential equation. It holds true. And we can calculate the rotational energy as well. So we can solve the Schrodinger equation for the rotation of this 2p electron. We get this total wave function as the product of the radial function and the angular function. If you look at the angular function, it's e to the power of plus minus I phi. So in this case, L is 1. M sub L is plus 1 or minus 1. Now let's look at 3D orbitals. In a two-dimensional world, there are only 2 3D orbitals, okay, instead of 5. Why? Again, in the two-dimensional world, we are looking at a angular momentum vector. It can only point up or pointing down. All right? There are only 2 options. So there are only 2 possible values for m sub L, because m sub L is the z component of the angular momentum. And this angular momentum can only be pointing up in the z direction or pointing down in the z direction. There are no other directions. So again, we make conjectures. We say, well, maybe it's this. This is for the radial wave function. We solve for the energy. And we can look at the Schrodinger equation again. And we can solve for the value of B. We can get the energy. So B is 2 over 5. The energy is negative 2 over 25. And again, for the 2... again, for the two-dimensional world, when you have a hydrogen atom, a two-dimensional hydrogen atom, when you are looking at the d orbitals, again, the angular momentum of this 3D electron can only be pointing up or pointing down. For the 3p orbitals, there are only 2 3p orbitals as well. So we can also solve the equation after making the conjecture here, and we can get the energy, and we can solve for the value of B. It looks tedious, but it's just an algebraic equation to solve, so it's not too bad. We got the value of B, we got the value of C, and we got the wave function for the 3p orbital. So this part is the radial function, this part is the angular function. So over here you can see there are 2 nodal surfaces. One is R equals 15 over 4. That's a spherical. Well, it's a circular nodal surface in the two-dimensional world. And the other one is a planar nodal surface, because you may combine this R with cosine phi to get X. You may combine R with sine phi to get Y. So in this case, when X is 0, you have a planar nodal surface. When Y is 0, you get another planar nodal surface. So it depends. It depends. If you have 3px, all right, you have the X planar nodal surface. When you have 3py, you have the Y equals 0 planar nodal surface. You can also look at the 3s orbital. Similarly, you can convert the differential equation to algebraic equation. You solve this algebraic equations. I want to show you the result. We got all those parameters, and you get the wave function here. This is the wave function for the 3s atomic orbital of the two-dimensional hydrogen atom. And you can see there are 2 circular nodes in the two-dimensional world. All right, just by setting this to be 0, you get 2 roots, 2 solutions. Now, just in general, if you're looking at a two-dimensional hydrogen atom, the principal quantum number can be 1, 2, 3, 4. L can be from 0 to n-1. M sub L, okay, over here, this is different from the three-dimensional world. M sub L can only be plus minus L, because, again, the angular momentum can only be pointing up or pointing down. 2 options. The wave function is the product of the radial function and the angular function. The radial function is a polynomial function of the radius times an exponential function. The exponential function takes this form. It's e to the power of negative 2r over 2 and minus 1. All right, so this is different. This is different. For the three-dimensional case, you have e to the power of negative r over n. All right, so this is different. And this f is a polynomial function of R. What about the angular function? It's e to the power of I m sub l times phi. So this m sub l can be plus minus l. What about the energy? The energy always takes this form. This is the energy. And then I'm going to show you the wave functions. 1s, 2s with a node, a circular node, 2p also with a node, a planar node, 3s, 2 nodes, 2 spherical nodes, 3p also 2 nodes, but 1 circular node, 1 planar node. Over here, 3d orbitals, 2 planar nodes. 2 planar nodes. All right. Okay. All these wave functions are the eigenfunctions of this Schrodinger equation for the two-dimensional hydrogen atom.